Good afternoon friends. Today we will discuss three continuous distributions, namely Cauchy distribution, Weibull distribution and Laplace distribution. So let us start with Cauchy distribution. Professor Gothi will discuss the Cauchy distribution and its characteristics.
Okay friends, first I start with the Cauchy distribution. So first of all we take definition. A continuous random variable x is said to follow standard Cauchy distribution if its probability function is given by 1 upon pi into 1 upon 1 plus x square, where range of x is from minus infinity to infinity and 0 otherwise. So this is the PDF of standard Cauchy variate, and in that case random variable x is said to be standard Cauchy variate. Here if we take, say, x is equal to y minus mu upon sigma, then we shall get the PDF of y, and it is, say, gy is equal to 1 upon pi into 1 upon 1 plus y minus mu upon, instead of sigma I just take lambda because sigma is standard notation for standard deviation. So, and if we simplify this into Jacobian, so that is 1 upon lambda, dx is equal to 1 upon lambda dy. So this is equal to lambda upon pi into 1 upon lambda square plus y minus mu square, where y is from minus infinity to infinity, mu is also from minus infinity to infinity, and lambda is positive and 0 otherwise. So this is the PDF of Cauchy variate with two parameters, mu and lambda. Mu is the shape parameter, whereas lambda is a scale parameter which is always positive. From this now I just want to find mean and variance of this Cauchy distribution. So if we want to find mean, say mean mu and dash, say, that is expected value of y, that is integral over the range, total range is from minus infinity to infinity, y gy dy is equal to lambda upon pi integral y upon this lambda square plus y minus mu square dy. To obtain this integral, let us add and subtract subtract and add mu. So y minus mu plus mu. So this is equal to lambda upon pi into integral y minus mu upon lambda square plus y minus mu square dy plus lambda into integral from minus infinity to infinity 1 upon lambda square plus y minus mu square dy. I just write this integral as, say, I suppose, plus lambda into, if we integrate this, then it is 1 upon lambda tan inverse y minus mu upon lambda. It is of the type 1 upon x square plus a square type. So integral is 1 upon a tan inverse x upon a type. So where this I is equal to integral minus infinity to infinity y minus mu upon lambda square plus y minus mu square dy. So this is lambda upon pi into I plus this lambda is cancelled, and tan inverse infinity is pi by 2 and tan inverse minus infinity is minus pi by 2. So this is pi, there is 1 lambda upon pi is there. So 1 upon pi, I just, this mu is there,
Second term.
mu into lambda by pi. So mu, so this is lambda upon pi into I plus mu, pi by 2 plus pi cancel, so mu plus this. Now actually the only problem is to obtain the value of I, and to obtain I, actually if it multiply and divide by 2, then we can get log of denominator type, and log of infinity and log of minus infinity are undefined, and therefore this definite integral does not exist. It is not a specific, so this is not absolutely convergent, and therefore we can say that mean does not exist, and therefore we shall go for its principal value. To find this, we take this way, say limit n tends to infinity, integral from minus n to n, y minus mu upon lambda square plus y minus mu square dy. So ultimately when we take limit as n tends to infinity, so it becomes minus infinity to infinity. Actually it is not the exact value as I, it is its principal value. So limit n tends to infinity. Now if we obtain its integral value, so if we multiply and divide by 2, then we shall get derivative of denominator in the numerator, and therefore it is log of denominator. So log of L square lambda square plus y minus mu square minus n to n. So this is equal to 1 upon 2 limit as n tends to infinity. This is log of, just replace y by n, then replace y by minus n and take the difference. So log of lambda square plus n minus mu square minus log of lambda square plus minus n minus mu, means I can write n plus mu square. So this is equal to 1 upon 2 limit n tends to infinity. This is log of lambda square plus n minus mu square upon lambda square plus n plus mu square, and so this is equal to, now log and limit can be interchanged, and so log of limit of this, and to find this limit we may take maximum power of n common. So there is one technique to find the limit as n tends to infinity. There are two methods. First method is just to take maximum power of n common from the numerator and denominator, or you may take y is equal to 1 upon n. So here I take maximum power of n common, so n square common, so in the bracket lambda square plus 1 minus mu upon n square, lambda square by n square. Here also n square common, so lambda square by n square plus 1 plus mu by n square. N square cancel, and as n tends to infinity, anything divided by infinity will be 0. So this is 0, these two are also 0, ultimately 1 upon 1 means 1, and log of 1 is equal to 0. So that conventional value of I is 0. So ultimately this is 0, and therefore mean mu 1 dash is equal to mu. So this is not the exact value. Actually mean of this distribution does not exist. But if you go for its principal value, then this is the conventional mean. So if we consider mean as mu, then we can find variance also. So say variance of y, that is expected value of y minus mu square, its conventional mean. So this is lambda upon pi y minus mu square gy dy, and therefore this is, here if we add and subtract mu square, sorry lambda square, so lambda square plus y minus mu square minus lambda square upon this. So this is now lambda upon pi into this upon this 1, So integral from minus infinity to 1 dy minus lambda square integral 1 upon lambda square plus y minus mu square dy. Now we know that we can find this value. In the mean also we derived this type of integral. But here we cannot find, because integral of 1 is y, replacing by infinity and minus infinity we get infinity. So value is infinite. So if expectation is infinite, means we say that expected value does not exist. So here in this case variance does not exist. Even if we go for its conventional value, principal value, say if you want to obtain this value, principal value of this, so we may write this as limit n tends to infinity, integral from minus n to n dy, say 1 dy, then limit n tends to infinity, integral is y, replacing y by n and minus n, ultimately we get 2n, and this is again infinity. So its conventional value also does not exist. So this way variance also does not exist. So for this particular distribution, mean and variance do not exist. Then we go for its characteristic function, say. So characteristic function, say phi t, I just obtained for a standard Cauchy distribution. So it is expected value of e raised to I t x, that is integral from minus infinity e raised to I t x fx dx, where fx is the PDF of standard Cauchy. So 1 upon pi integral minus infinity e raised to I t x 1 upon 1 plus x square dx. So actually this is a complex integral, and it is the case of contour integral. So actually the contour integrals is not the part of the syllabus up to TYBSc even, and therefore I just write it is, if you obtain by complex integrals, this value is e raised to minus mod t. Even otherwise also, if characteristic function is this, then by inversion theorem we can find PDF also. So here characteristic function of standard Cauchy is this. Now if you remember, in 12th standard we have studied this, that function fx is equal to mod x, say, is continuous at x is equal to 0, but not differentiable at x is equal to 0. So here it is the same case, it is mod t. So derivative of e raised to minus mod t is not differentiable at t is equal to 0. Generally when we differentiate this and put t is equal to 0, then this value 1 upon I into this will give you first moment mean. But since derivative at t is equal to 0 does not exist, we say that mean of this distribution does not exist. Second thing, if we take, say, x is equal to y minus mu upon lambda, or in capital notation if I write, say, x is equal to y minus mu upon lambda, actually this is the characteristic function of x, standard Cauchy variate. So from this we can get characteristic function of y. So say phi yt, characteristic function of y, that is expected value of e raised to I t y is equal to expected value of e raised to I t, y means mu plus lambda x. So this is equal to e raised to I t mu, which is constant, and expected value of e raised to I t mu x, and therefore this is e raised to I t mu into characteristic function of x with parameter mu t, t lambda, sorry, this is lambda, so e raised to lambda t. So this is equal to e raised to I t mu into e raised to minus t lambda. So ultimately it is e raised to I t mu minus lambda is positive. Actually mod t lambda is mod t into mod lambda, but lambda is positive, so mod lambda is lambda into mod t. So this is the characteristic function of Cauchy variate with parameters mu and lambda. Now we want to obtain the distribution of sum of independent Cauchy variates. Suppose we have n in, so we consider this as a theorem. Suppose y1, y2, yn are n independent Cauchy variates such that each yi is Cauchy variate with parameters mu I, lambda I. So all yi's are independent and they all are Cauchy with different parameters mu i's and lambda i's, I running from 1 to n, and we just want to obtain the distribution of sigma yj, j running from 1 to n. So since all yi's are Cauchy variate, as we saw here, the characteristic function of yj, say phi yj, is e raised to it mu j minus lambda j into mod t for all j running from 1 to n. Now if you obtain, actually we have to obtain the distribution of sigma yj. So let us obtain the characteristic function now of sigma yj, that is phi sigma